Hi everybody, how is everybody this morning? My name is Geordie. I see a lot of familiar faces and some new faces, so if I haven't seen you guys in a while, hey, how's it going? And if I haven't met you yet, hopefully I'll get to later today. Just before I begin, this is going to be a little bit different than likely the other presentations that you've seen. I'm going to keep this very conceptual level because the topic I want to talk about can get quite complex when you get into the details, but I think that the most important part about this is the underlying concept, because it's absolutely fascinating, and I hope to be able to share some of my enthusiasm for this particular topic with you today. This is connected to this conference in a couple ways. The most obvious one is that, as I'm sure you've heard, the machines that we build are designed to solve optimization problems. And it turns out that the adoption of these ideas on a large scale is somewhat or maybe primarily hampered by the fact that actually doing what I'm going to show you at scale is extremely hard, because there are very hard optimization problems you need to solve to do what I'm going to talk about. So before I get into it, has anybody ever actually seen this specific image before? Like this specific image? No? Okay. Does anybody want to hazard a guess as to what that is? What does it look like? Apple, okay. So let's think about this for a second. You've never seen this thing before. It doesn't look anything like an apple looks in the real world, but somehow it has some characteristic of apple in it. And that is an absolutely fascinating observation to me, that the way that humans, and in fact I think all creatures that share some of our biological structures in and around our heads, we have this capability of distilling an enormous amount of information about the world into a small number of concepts. And so what I'm going to talk about is recent work that we and others have been doing on how to make that work with a machine. Just before I do that, I wanted to just lay some groundwork. Actually, I'm connected to one of the machines at D-Wave right now on my laptop. I was hoping to actually show you some things, but apparently because of the format, we can't do that. But if you want to see some of this later, I'd love to show it to you. But I wanted to, this is kind of breaking news, I suppose. We haven't told anybody this yet, but this 512 qubit version of the chip that we're building, we actually got it to run last week on roughly 200 variable problems. So that green dot there is the new data point on this scaling curve that goes back all the way to 2002 when we first started building these things. Probably the most advanced piece of technology that we've built that is actually available for general use is now at the Information Sciences Institute at USC in Marina del Rey, and any one of you can use it. This picture is Daniel Ladar, who I think is here. Is Daniel in the crowd? Ah, he left. Hope it's not correlated with my talk, but maybe. And this other guy is Yanis Yortsos, who's the dean at the Viterbi School. And that machine right there in the background is the actual physical machine. So, you know, this thing is, this quote that he pulled out is about optimization and machine learning, but as any of you know, and I think that there's two basic reasons why people get interested in quantum computing. And I don't mean once you become an expert. I mean when you're like a high school student and you're saying, oh my God, that's the coolest thing I've ever heard. So there's two kind of categories of, oh my God, that's the coolest thing I've ever heard. So one of them is primarily physics-based. So a lot of people get into this field because they're entranced by this idea that we can somehow build or understand things that are somehow fundamental. They reach down deep into the guts of the universe and they pull out this wonderful stuff. And whether you agree with him or not, this guy is a very strong proponent of this wonder of physics. You know, parallel universes and infinite, or not infinite, I suppose, but very large numbers of possible things all coexisting. And I think this is a wonderful idea. I have no idea whether or not it has any truth to it, but I think it's a neat idea. There's another train of thought that brings people into this, which is a little different, and that's using these machines to compute things that have never been computed before. And My experience with this community has been that those two types of drives are not always the same. They're not aligned always. So I think that they're very distinct. So from the perspective of our project, we have a mix of both. We have to be a little mercenary about the way we do things and concentrate more on this kind of thing than the first. But what I'm going to talk about today is something a little different than both of those things, and it has to do with maybe more the second than the first, and that's, okay, well, let's assume that you had something really cool, a machine that you'd built that did something new. What would you do with it? And the standard answers that people give for quantum computation when people are talking to reporters or the funding agencies and stuff are very unsatisfactory to me. I really don't care about code breaking. I could care less, really, to tell you the truth. It's not interesting at all to me on any level, intellectually or from the perspective of business. Quantum simulation is pretty cool, but having been involved in the actual practice of how that works in industry, it's like pushing boulders up hills. I mean, it's really hard because that whole industry, in particular drug design, has its roots in industries that are hundreds of years old, and there's a lot of inertia in that world, and moving over into highly numerical stuff is hard. So my thing, one of the things that I've always been interested in is the idea about, like, why is it that building machines that mimic human behavior is so hard? And when I was in high school, I ran across this guy who was building a company called Thinking Machines out of work that he'd done at MIT. And I become fascinated with the whole subject, and he kind of kick-started my interest in this whole thing. More recently, in my professional life, I ran across Hartmut, who's a fascinating guy, and he has, asked a lot of interesting questions over the course of, my knowing him. But I think this one goes to the heart of something that I find really interesting, is that wouldn't it just be awesome if somehow you could build a quantum computer that solved a really hard problem at the heart of cognition? Wouldn't that be awesome? I mean, let's forget about whether you can or not. If that turned out to be true, that would be an amazing thing. Now, what I'm going to show you today is a potential example of one of these that I'm very excited about, and I've been spending most of my time working on. It's not a new idea, so these ideas have been around for a while. Those of you who are more mathematically oriented may recognize that the compressive sampling part, or compressive sensing, rose fairly recently out of the work of Terence Teo and some others. But this guy, I think, is more my kind of mentor on this path, this Andrew Ng guy. He has some wonderful content on the internet and video where he describes these ideas in extreme clarity, more than I'm going to be able to, and I highly encourage anybody who's interested by this topic to look him up and listen to him speak about these things. But the thing that I'm going to talk about specifically is this idea that human cognition, all of our sensory input seems different. We've got vision, sound, and touch, and taste. But there's evidence, and I think fairly compelling evidence, that what we actually do under the hood may be driven by a single algorithm. And so progress in understanding what that algorithm is and how it works has very significant impact on the field of machine learning, and more generally, I think, on humanity. So I'm going to go over some examples of how this might work. So this is Eddie Farhi on the left, and here's an image of him. If you know Eddie and you look at this picture, within a fraction of a second, the label Eddie Farhi pops up in your head. And this is related to the Apple example that I was talking about earlier. So how is it that you know it's Eddie Farhi and not Angelina Jolie? Because if you see her, that other thing goes off in your head, the object detector that has the label associated with it. So how does this work? Well, it can't simply be the raw data. And we know that from several different perspectives. You have roughly 10 to the 17 photons hitting your eye every second. The amount of raw data entering into your sensory input systems is mind-bogglingly vast. How is it that you can do this? So the understanding of this has been evolving quite quickly over time, and the most likely candidate for all this is that the raw data gets processed by what you might think of as filters, very special kinds of filters that in some sense optimally compactify the incoming information. So these things in the machine learning community are called features. So I've shown a particular type of feature here, which is called a Gabor wavelet that Hartmut uses quite a bit in his work. The idea is that when an image impinges upon the machine, what gets sent into the algorithm is not the image. It's a processed version of the image that's being sent through these little filters. This isn't true just for vision, it's also true for sound. So you don't send raw auditory files into machine learning algorithms. You send processed files that have been decomposed into these feature spaces. It's also true for text. If you take a book, you don't send the book in its raw text form through the machine learning algorithm. You send features, which are extracted in a variety of ways. So I'm going to now enter into the specifics of what we're doing. And I'm going to start by a very simple warm-up exercise, which hopefully conveys one of the key messages that I want to talk about. So imagine you have a video, and in this specific case, let's say it has 8 images. And let's say the 8 images are exactly identical to each other. And for some reason, you have a fascination with apples, and you really want to download this movie from Netflix and watch it over and over again. So let's say you're Netflix. The question I'm going to ask is, how should I send you this movie? Now, I'm going to give you 2 options. Now, of course, there's many others, but this is just to illustrate a point, right? So one of the ways you could do this is you could write down each of the images as a series of pixels, color values, all 8 of them, and ship all of those bits, okay? And if you do that, you count the number of bits in these images, it's almost 2 megabits. So here's another option. Since the images are all absolutely identical, you don't need to send all 8. You send one of them, and instructions that in the 8 sequences, I want to turn on that one image. So this vector of ones indicates, please turn on this image, please turn on this image, please turn on this image. And because they're all the same, this is equivalent to sending the other one. This is completely lossless compression, okay? Now, with 8 images, of course, who cares? But let's say it's a data feed from a security camera. And the security camera is monitoring a facility. And let's say it takes 30 images per second, and over time, nothing changes over 24 hours. Do you want to be shipping every single image? No, of course not. You can ship one image with instructions that it didn't change over the whole time. Now this is a limiting case where everything is identical. These things I'm going to refer to as features, or equivalently dictionary atoms. So these are going to be the substance of the core of what we're going to try to find. Now this, depending on what your background is or how you're thinking about this, this might be either completely trivially obvious, or this might be actually kind of a deep observation. And I actually think it's both, of course. It's trivially obvious because we know that 8 things identically is the same as 1 with instructions to send 8. But there's a deep underlying thing going on here. And if this gets confusing, go back to this example and think about it. So now I'm going to make it a little bit more interesting. Now, when we look at the world around us, we have constantly video streaming into our brains somehow. Or if you have a big movie, you've got a bunch of frames. Maybe if you're talking about big data sets, it could be billions of images. So the question I'm going to ask is, we only needed 1 feature to reconstruct that silly movie, but how many features do you need to reconstruct all movies? Okay? So what I'm asking is, what is the smallest feature set from which you can reconstruct every natural image? Yeah? So what I'm talking about is distilling the essence of all vision down to a limited number of features. And I want to know, what is that number and how do we find it? And more interestingly, how do we find the features in that set? So what I've got here is a marginally less silly movie, still about apples, but the images are not all identical now. They share some characteristics. They have green in them, but they're not identical. So let's start by doing maybe the simplest possible thing we can imagine. Let's say we only had 1 feature to represent the entire universe of images, and in this case, this little Apple movie. you can probably intuit that you can't do very well at reconstructing it with only one image, because all that means is the image is either on or off in every frame. So you're never going to reconstruct even one of those guys right. You can think of this feature dictionary with only one image as kind of like an average of all of the video that this thing has seen. It's not very good. However, there's another limit, which in some sense is just as silly, where you send a feature for every frame in your video. This you can think of as memorization of the world. So if when I'm scanning through the crowd, every time my brain takes a snapshot of what's going on, I store the entire snapshot as a feature. That would be this. And in this case of this Apple movie, the idea would be I have 8 features. And for image 1, I turn on the first one, but not the others. For image 2, I turn on the second one and not the others, and so on and so forth. So these are 2 limiting cases, 1 and a ridiculously large number of them. But what about in between? So a lot of the ideas that I'm going to be talking about now are motivated by this, that natural objects in the world are not random. You know, if I were to show you a bunch of random images, none of this would work. But the things that we look at are not. They have a structure. Objects are contiguous and so on. So here's a reconstruction of this little video. This is actually only a part of the video. I pulled out 8 images of a 256 image webcam stream. So now if I have 2 features, you notice something now that's a little bit more interesting. So you see these images over here that have the black bits at the top now have black bits in the reconstruction. And the reason is that we now have a feature that has black at the top. So we have the option now of turning that on or off when we reconstruct the original video. And as you see, the reconstruction is still not very good, but it's captured some new thing about this image. 4 gets a little bit better. So if I go back and forth, you see there's 2, there's 4. So it's got a little bit more contrast in the top part. Here's 20. That's a little bit better still. Here's 40. So with 40 basis images, that's these guys, I can with almost perfect reconstruction reconstruct this 256 image movie. So we've taken 256 images and compressed them down to 40, where every member of the 256 image set is a linear combination of these basis images. Okay? Now, this, of course, is not just for apples. You can do this with any information. There's my face. So this was inspired by a data set called the Frey Faces data set. A guy named Brendan Frey moves his face around, and you want to try to do things with it. So this is a 20-element dictionary for a 256 image movie of me moving my face around. There's my colleague Suze Gildert. Now, that's fun, but it's not what we're after here. What we're after here is not only unlabeled data, but mixtures of unlabeled and labeled data. Because if I show this thing a bunch of pictures of my face, it may learn that there's something underlying those images that's the kind of the distilled essence of what it understands about me. But I also want to tell it it's me. So this is another example that we ran, where now there are 8 different objects in the computing things universe. Everything from me to Muck Muck there on the right. And the way that labels are used in this framework is really simple. So when you use this framework, when you're storing images, you use pixel data to represent your images, which are just real numbers. They're integers, between, say, 0 and 255 for a color channel. All you need to do is append to that image data a bunch of labels. So, for example, you can say category inclusion labels, where +1 means the object is in the category and -1 isn't. So if I were to take an image of my face, I just append an 8-bit vector to the end of my description of my images. So my image is not only now a bunch of real numbers which describe the pixel data, but it's now that concatenated with a bunch of labels. Where this image has me, but none of the other things. And so this is an example of doing that. So in this experiment, we ran eight categories of objects, the ones I showed you, with 128 images from each. So this is 1,000 image movie. And for each of the data sets, we labeled half of them and left the other ones unlabeled. And we only used 10 features, and here's what they are. So just think about this for a second. So with 10 features, there are 2 to the 10 possible reconstructions from turn them all off to turn them all on simultaneously. So there's only 1,000 possible images that this thing can generate, and I'm going to show you the reconstruction. Look at that. So that's the top. So the top one is the original image data from a subset of these movies, and the bottom one is the reconstruction. Each of these reconstructions is a linear combination of some subset of these 10 dictionary atoms. Isn't that amazing? So the reason for this is extremely deep, and it has to do with these ideas underlying compressive sensing and the amazing amount of structure that we have in our world. But I find this absolutely fascinating. With just 10 features, you can represent nearly 1,000 images with quite good reconstruction accuracy. So I tried to do this without doing any equations at all, because I wanted to be conceptual, but that's not satisfying. So I'm just going to do a very brief overview of how this works under the hood. And it's actually kind of at the high level, kind of simple. So these dictionary atoms, these features, you can think of them as vectors of real numbers, where the vectors are the values of the pixels. So you start at the top left-hand corner of an image, you write down the 3 pixel values for, say, RGB values there. Move over 1, write down those, move over 1, write down those, make them into a big long column vector, okay? So these D's you can think of as just column vectors of real numbers. These W's are bit strings that tell you which of the atoms to combine. So what this is saying is a reconstructed image, which is this guy, is a sum over a linear combination of some of these dictionary atoms, but not others. So in the case of this particular reconstruction, that reconstructed face there combines 2, 4, and 7, and none of the others. So if I were to take dictionary elements 2, 4, and 7, add together all of their pixel values, that's what you get in that reconstruction. Okay? So what we're trying to do is in some sense very simple. What we want to do is take every reconstructed image, which is this eye guy, and try to minimize the distance between it and the actual image. So what does that mean? So the actual image has a bunch of pixel values. The reconstructed image has a bunch of pixel values. Subtract the square of the sum of all of the pixel values. So pixel 1 has 3 numbers. Pixel 2 has, image 2 has the 3 numbers. Sum over the squared difference of all of them, sum over all of the pixels, sum over all of the images. Okay? So when you do this, you generate what's called a loss function. And what you want to do is try to minimize that function. You want the reconstructions to look as much like the original images as you can. And there's a large number of extremely hard discrete optimization problems that are generated through this process. So when you try to solve for this optimization problem, you get this monumentally large number of, it's not so large that you can't do it, but it's so large that it stresses the capabilities of where we're at today in modern computing infrastructure. And you could probably do it a lot better if you had a faster discrete optimization solver, which is kind of like where it connects into the hardware that we're trying to build. Okay, so that's all great and fine and whatever, but so what? Let's say that every image in the entire universe of Google images, say there's like 100 billion of them on Google. Let's say that every one of those images could be generated by using 1,000 dictionary elements. Okay, so there's 1,000 images where every single image that's on Google is a linear combination of that set. Then every image in the Google repository can be described by 1,000 bits, right? So that's one important point, is that compression is, I used to think compression was kind of just this boring thing that you did with the JPEGs and stuff. It's not. Compression is really at the heart of a lot of the issues surrounding what it means to understand something. So the more that you can compress something, the more that you understand it, I think, is one way of thinking about this. So the first thing is being able to do this on large scales enables vast compression. There's a substantial fraction of the data that flows on the internet that comes out of Netflix. If you could do this sort of compression on video streams, it's an enormous deal for people who send a lot of material over the internet, specifically video. A couple other things you can do with this thing. So one of them is all of the kinds of things that machine learning people do now, all of the algorithms require features. You can either provide them as a human or you can try to learn them from your data, but features drive machine learning. And it has to do with the stuff I was talking about at the beginning of the talk, where raw data is not what's processed by these algorithms. It's something that's distilled from the raw data. So what are those things? How can you make them better, smaller, more sparse, more meaningful? So things like object recognition in images. You have a rover, say a Mars rover, needs to have some autonomy. And it has some sensors on it. If you can develop a very sparse set of features that discriminates between, holy shit, I got to run away from this thing, or, oh no, everything's all right, then you can deploy those things remotely on things like robots. So this idea of finding extremely sparse representations of the things that you like to classify is also a very important part of this. Things like anomaly detection. So you might imagine that these things learn to represent the images that they've seen. So one of the things you could do is show it images of chest x-rays of healthy people. Thousands, tens of thousands, hundreds of thousands of chest x-rays of people with healthy lungs. And it will learn a basis set for reconstructing all of those images. If you now show it an image that isn't healthy, it has things in it that it hasn't seen. And what will happen is it will poorly reconstruct that aspect of the image, which is an anomaly, which is something that you're going to be looking for. It's something that's not like what I've shown it before. And anomaly detection is important across a whole bunch of different industries, including intelligence community, defense, and healthcare. There's a bunch of other things. But one of the things that I think is the most cool of all of this is the use of these things in generative mode. Okay, so what does that mean? So usually in machine learning, we're used to thinking about classification, say. So I bring you an image, and you assign labels to it. So I give you an image, you tell me whether there's a car in it. But there's another way you can do it with this algorithm, which is the inverse problem. So instead of giving it an image and asking it for a label, give it a label and ask it for an image. Okay? So think about that for a second. So let me, instead of giving you all of the pixel data and asking you to fill in the labels, I'm going to give you the labels and ask you to fill in the pixel data. I have a demo of this on my laptop. I can show you this later. But what the demo I built does is it takes the dictionary elements from those movies that I distilled down, and it randomly turns on bits in a sequence like a movie. And it's, I think of it like dreaming. So imagine this thing knows nothing but apples because that's all you've ever shown it. Its universe consists of apples. Now, it goes about its life observing the world, recording information about apples, forming its dictionary elements. But then in the quiet of the night, when it's relaxing in the garage, and you turn it the other way and you say, please generate what you think an apple is. It will turn on the bits of the dictionary randomly, sum them up, and generate sequences of images that it thinks are correlated with apples. So Jeff Hinton, a very famous machine learning guy who is involved in research like this, calls this hallucinating. But I prefer the term dreaming because I think it's a little bit more evocative. This guy is Douglas Hofstadter. He's a brilliant guy and I very much admire his work. And one of his main threads that goes through his research is that creativity, in the sense of being able to generate things not using brute force prescriptions, is a very key element to understanding cognition in humans. And this type of machinery allows you to generate things that have never been seen before in the world, like a new version of an apple, which is formed from these combinations of these dictionary atoms. That thing that it's generating has never been seen before, but it has the characteristic of apple. Yeah? So I think that this is a very interesting way to proceed in this, this idea of trying to build more and more human-type machines. Okay, thanks.
Questions?
So as you build more and more human-type machines, you think you can avoid some of the pitfalls that humans have? That if you're watching a security screen for 24 hours, the human falls asleep, or the way an animal is designed to look for specific things, like something it's going to chase, and the animal, the thing it chases, stands still and it doesn't see it anymore. So presumably you would be able to dial those effects more or less. Have you thought about those issues?
Well, the one that we have thought about a little bit is the video camera surveillance thing, because for a bunch of different perspectives, but that one is kind of an unnatural thing, that biological systems don't stare at things for years without moving or sleeping. But that's a good fit for this type of thing, because what you can do is in an online way keep adding images to this repository that you learn from, and consistently keep changing your dictionary to keep reconstructing what it's seen. But if it sees something anomalous, it'll flag it immediately. So if an image comes in that it can't reconstruct well with the dictionary it's got, it'll say, hey, I haven't seen this before. So if a car moves by and it's never seen a big black thing in the middle of the image, when it tries to reconstruct using the dictionary, it doesn't have any features of big black things in the middle. So what it'll reconstruct is the thing without the car. This is kind of a neat thing when you do this for real, is you can take video and then reconstruct it and completely remove objects that it hasn't seen in the reconstruction. But the way that you would use this in this case is you delta the two, and look, there's something there that wasn't accounted for. In terms of the analogy with biology, you can take this too far. I mean, I like to wonder about what's possible and think about big things, but practically what's happening here is all we've done is taken very small video clips and compressed them in this special way. And I think it has a lot of promise for the future for enabling research in those types of directions, but it's nowhere near there yet.
And actually, you mentioned the anomaly detection. What popped to the top of the stack was the technique of, you have a car alarm, which is sensing for an anomaly, and it's apparently a very common technique to, somebody comes and just jostles the car, it goes off, you go reset it, you do that procedure 10 times until the person says, something's wrong with my alarm, they turn it off.
Yeah.
And then the car is gone.
Yep. But so in that case, if you were learning from experience, what this system would learn is there a correlation between jostling and entry? And if there was no correlation between those two, it wouldn't trigger an alarm on jostling. It would learn that when entry was preceded by a certain set of behaviors, and it would try to distill what those behaviors were, and it would give you an accurate, subject to the data being good, classifier.
So at NASA, we think a lot about, telescopes looking into space, and we get very faint signals back with very few photons. And in fact, most of the information we have, most of the data we get is from satellites that are looking down at the Earth. That's where the vast majority of all of the data is coming from. And now we have these Earth-observing satellite systems that are recording hyperspectral data that there's so much of it we can't even analyze it in real time. So maybe this sort of compressed sensing would be applicable for us especially.
Yeah, absolutely. I think that in any situation where you're overwhelmed by the amount of raw data, using a strategy that's similar to the way that we probably you'd use that, we have too much raw data coming into our eyeballs, hitting our retinas. We have strategies for dealing with that, which compresses the data into a particularly meaningful basis. So biological systems find things like tigers especially meaningful, But when you're crafting an algorithm, you can create category labels that define what you mean by meaningful, and then try to find the smallest subset of features that give you good classification accuracy on what you're looking for. So if you're looking for something specific, or the lack of something, or the correlation between two things, you can design your system to kind of mimic the way that humans would behave to, say, a tiger. So when I see a bunch of photons that's indicative of tiger, I know I'm in trouble. So instead of being, photons being indicative of tigers, you can say gyroscope data being indicative of something blowing up or something like that. So there are ways to use these things in any situation where you have a ton of data, most of which is extraneous.
More questions? I have one, maybe it's naive, but it's more technical as well. So you showed us this, number of pictures of an apple, and those were kind of pretty simple pictures in the sense that if I were to compress them with a simple, compressing algorithm, then I would reduce the file by a large amount.
Yep.
Now the basis images are much more complicated.
Yes.
So what happens, when you factor the things in? Is it still much more efficient to work with the basis images than?
So at the high level, I think that the answer is the more structure, the more similarity there is between the images in your initial file, the better this works. So if every image is completely unlike the others, then you go into the limit of having to have one dictionary feature per image. So for example, let's say every image was completely random and completely uncorrelated. That would be a bad situation. If every image was the same, that's good, and everything in the real world is somewhere between those two. So it's kind of an unsatisfactory answer, but the evidence, both empirically and theoretically, seems to be that the more similarity there is in the initial objects, the better compression you get, which makes sense.
More questions? So if not, let's thank all the speakers of this session again.
Thanks.